All right, let's see how this goes. I want to read another paper today, getting ViT in shape. I think it came after party 3, which is the last one I covered. We'll see how much time I have. Kids might come back anytime, and there might be echo, and there might also be dishwasher sounds in the background. But hey, we'll do what we can. I'll share this tab, and let's get reading. So, just to recap, this is yet another paper in the series that we're going through from clip to polygamma. Last time we covered poly 3, and this is an optimization of visual transformers. So getting ViT in shape, scaling laws for compute optimal model design. Scaling laws have been recently employed to derive compute optimal model size for a given compute duration. We advance and refine such methods to infer compute optimal model shapes, such as width and depth, and successfully implement this in vision transformers. Our shape-optimized vision transformer, ViT, achieves results competitive with models that exceed twice its size, despite being pre-trained with an equivalent amount of compute. For example, ViT 14M14 achieves 90% fine-tuning accuracy on this data set, surpassing much larger ViT G14 and approaching ViT G14 under identical settings, which also less than half the inference cost. Conduct thorough evaluation, multiple tasks such as classification, capturing VQA, and zero transfer, demonstrating the effectiveness of our model across a broad range of domains and identifying limitations. Overall, our findings change the prevailing approach of binary scaling vision models and prove the path. Okay, so by fiddling with the shape of the model, they get much better performance at comparable comparable performance at much improved efficiency. The de facto approach for improving performance of vision language models today is scale larger models are trained on more data for longer. Empirically, it has been observed that the benefit of scale often follows a predictable power law in which the performance f of x, like an error rate, satisfies this. So as one varies the scaling dimension x if the remaining dimensions are not bottlenecks. Here is irreducible loss. Right. However, the simple power law relation becomes more complicated when compute is considered. In this case, power laws are observed only along the compute optimal frontier. Otherwise, scaling of the model for model size for fixed compute budget can deteriorate performance. Right, so if you have a really big model and you don't train it long enough, you'll get worse results than having a slightly smaller model that you train enough. Since one often has a fixed compute budget in mind, one should pick the model size with maximized performance subject to compute budget constraint, which may imply not training until convergence. Indeed, this approach was used successfully in the recent chinchilla that outperformed predecessor gopher. I thought chinchilla. Okay. Training compute optimal. Yeah, I thought chinchilla, but older, 22. Okay. Oops. Good. Where are we here? Fortunately, in both of these papers, among others, the size of the model is related with parameter count, with no special consideration for model shape dimensions such as depth or width. So depth is how big each layer is. The rationale behind this choice follows from the surprising observation that the transformer shape had little impact on its scaling behavior and language modeling when performance is measured upstream. Nevertheless, follow-up analysis suggests that shape plays a pivotal role in other domains, such as machine translation, and also in language modeling for downstream performance, downstream like fine-tuning. Recent work, even of again upstream aspect ratio, such as single wide attention layer. In vision, in convolutional neural networks pointed out that parameter count is indeed poor predictor of performance. For example, scaling all dimensions in resonance is more effective than scaling single dimensions, such as depth. In addition, scaling width is often more effective than depth, especially for small models, hence optimizing the shape of transformers seems worthwhile. Okay, so they're saying that like at the time this paper was published, which was January this year, the common assumption is that shape, it's all about parameter count. And they said, that might be true in some domains, but not in others. So in translation and also in vision, it seems like shape of the network is important, not just the parameter count. In this work, we present Solvit, a shape-optimized vision transformer, and it matches the performance of much larger models despite being pre-trained with equal compute. It is derived from a recipe we introduced for optimizing the shape of neural architecture, such as their depth and width. A principled approach for scaling multiple dimensions is advantageous because although one can scale dimensions via brute force search, this requires extensive computation. Our recipe allows us to extrapolate without having to conduct intensive experiments. For example, after only 115 experiments, we identify a scaling strategy in ViT for all 3 dimensions: width, depth, and MLP size. For comparison,